Okay, so I don't generally do this kind of video, but I wanted to chip in on something I've found out about the GTX 980 Ti reference PCB. This is from a EVGA GTX 980 Ti. By the way, RIP EVGA, you will be sorely missed. And I've seen a lot of other YouTubers that kind of do PCB level repair, mostly like Buildzoid, talk about how this VRM is very problematic and these phases tend to die. And this card, I'll have a few pictures up on screen once I edit the video, had exactly this problem where this last phase down here blew up and I had to replace it. And it blew up in a very specific way where it basically welded the switch node to the PCB. And I've seen that's kind of a problem with these DRMOS power phases, power stages that tend to have pretty bad heat dissipation because the switch node is huge, eats up some of the useful area, so it doesn't dissipate heat as well through the PCB. But this still doesn't explain why this area would die so much more frequently than the rest of the card. Because that's what I've been seeing on dead cards online and in videos. Also, I was really curious, so I found this for 50 quid on eBay with pictures that detailed, yeah, it has a dead VRM, and it was in exactly that position. So I was like, okay, I'm going to buy it, and I'm going to see if I can rescue it. I had a GTX 970 where I could harvest power stages that were good. And so here you can see an attempt by the previous owner to replace all the thermal pads, but that did nothing. Basically, the car still blew up. So he was aware of the issue, and then he sold it when it died. So here's the thing. You can see I've marked on the PCB some specific areas of the VRM, and this was to kind of find a relationship between which phases are hooked up to which power connector and the PCIe slot. Because remember, the card can take 75 watts from the PCIe slot, 75 from a 6-pin, and 150 from an 8-pin, or at least that's according to spec. And this card would get pretty close to that limit because it's a 250 watt TDP. So here are the three shunts, 1, 2, and 3. I'm sorry if the camera can't focus really well, but again, I'll have pictures on screen once I edit the video. And the thing I've been looking for is how many of these phases are hooked up to each one of them. And by looking at it, I could figure out that these top two phases are hooked up to the PCIe slot. Let's see if I can prove that to you, because this is the shunt for the PCIe slot. And I can, yep. So, okay. And it's going to go down to 0 ohm. These two phases are hooked up to the 6-pin PCIe shunt, which is up there. And again, we're going to go down to 0 ohm or thereabout. And, oh, of course, as a proof, if you check the first two phases to the 6-pin, it doesn't do anything. And even to the 8-pin, but trust me, that's the thing. Then VMEM is hooked up to 8-pin and PCIe, but that doesn't consume very much at all. This phase right here is hooked up to the 6-pin shunt again. So let me see if we can test that real quick, because it's kind of difficult to do one-handed, as you can expect. And I'm sorry, I don't have a tripod or anything, so this is why the video is going to be a little bit shitty. So yeah, you can see that's hooked up to 6-pin, but then these last three phases are hooked up to the 8-pin. And I think that's pretty clear, right? What's happening. The card will basically try to shove 150 watts through 3 power stages. And okay, these are 60 amp power stages, but that means they're pretty much getting redlined. And the thing I couldn't figure out was, in the original reviews of this card, everyone was saying, oh yeah, the VRM can handle 60 by 8 times, so that works out to 480 amps. And it's a lot, it's never gonna blow up. But here's the thing. These 3 power stages are taking the brunt of the power. So one thing we could experiment with is changing the shunt resistor arrangement, which is what I want to do with this card today, and see if I can make these run less hot. And then this mid plate for the EVGA card turns out to be one of the worst offenders because of check the thickness on thermal pads, and even if you use the right thickness, sometimes it doesn't make proper contact. And even if it did, this thing really doesn't add any surface versus just the regular PCB. So the experiment I want to run is removing this completely, because it doesn't really do anything other than impede air from the cooler from reaching the card itself. And then simultaneously hacking the shunts so that I have a little more power flowing through the 6-pin than I have through the 8-pin. And I mean, the connector will handle it, because the extra 2 pins, for those of you that don't know, are just 2 extra grounds that do absolutely nothing. So the current handling capability is strictly related to what your power supply can deliver, which I'm using a daisy chained cable, so that doesn't really matter. And that's about it. Now I will try this and see how it goes. So we have these 3 power stages, 1, 2, and 3. You can see I've marked them with my marker here, that are connected to the 8-pin connector shunt, which is this one right here. This one is for the 6-pin, and this one is for the PCIe slot. And since, again, we have 75 watts that can be pulled through our 6-pin, and 150 that can be pulled through the 8-pin, the card is probably balancing this incorrectly. So what I've been thinking is we could do the reverse of a power mod, power shunt mod, where you would usually short or reduce the current, so reduce the resistance of the shunt, so that the card sees less current and allows you to hit a higher power target without knowing. We're going to do the reverse of that and then edit BIOS to recoup some of the performance. So how does this work? Well, we have the 8-pin connector, right? So we have our connector here with part of it goes to ground and another goes to plus 12 volt with the max capacity of 150 watt by design. The connector can actually handle way more. That's been tried many times, but that doesn't matter. But it'll come handy later when we try to push some more performance through the 6-pin. And basically this is then connected to the shunt resistor, which is 5 milliohms, and is indicated, as you can see, with a R005. So here it is. That's the code for 5 milliohms. And this then goes to the 3 power stages, which are DR MOS 60, I think it's 6820A, right? 6820A. And each one of those is 60 amps max. But you can see that if we're drawing 150 amps through just these 3, then we're pretty darn close to the maximum, especially now that I've replaced one of the power stages with a lower capacity 40 amp power stage, because that's what I had. I harvested it from this GTX 970 with a dead core. And here you can see the power stages I removed, and one of them is still on there because I didn't intend on removing all of them. I just pull off the ones that started floating on the PCB when I heated up with off air, but it doesn't matter. So the plan here is to have the card think that it's pulling more power than it actually is through this shunt. Another thing that we could do would be rewiring the power stages, but that would involve extensive PCB modding, and I'm not going to do that. So getting into the explanation of how that works, we're just going to use Ohm's law, which says that voltage equals I times R, so current times resistance. And this voltage is what the controller on the card is looking at to determine how much power is going into each section of the V-core, basically, of the VRM. And I mean, 2 phases on PCIe seems reasonable because that's 75 watts, but still the phases can pull more power than that, but you'll never get there. But if you do 75 divided by 2, then you're getting to 37.5, right? If I'm not mistaken. Anyway, something just below 40 watts. But per power stage, which is decent because at 1 volt that's just under 40 amps, which is what we want. And on the 6-pin, that's even lower because it's pushing 75 watts on 3 power stages. So 1, 2, and 3, meaning that these only get 25 watts. And then we get to the bottom ones that are eating through 50 watts each, and that's unreasonable. So what we want to do is make the card believe that this resistor here is the same value, okay, because we're not editing the controller on the card. But what we could do is remove this resistor temporarily. And so if this is the original resistor, we're just going to lift one of its legs and then attach a couple of identical resistors which are in parallel with themselves, but in series with the first one. And these 2 connections are then going to go here and here. Now, I'm designing it like this because all these resistors would be 5 milliohms, and that's going to make sense in a second because I can harvest them from this card. Here we have one, and here we have another for the input connection. So if all of these are 5 milliohms, so remember R005, then this section here is in parallel and is exactly half of 5 milliohms. So this part here is equivalent to 2.5 milliohms. And this is a total of 7.5 milliohms. So we've just increased the resistance by 50%. And that should then increase the voltage by 50%, thus reducing the power target to 66% of the original. So we are reducing 150 watts to 66% of the original, which is, I'm going to type it here, 100 watts. Okay, so we're going to be pulling 100 watts through this one, and 100 divided by the 3 power stages gives us something in the region of 33 watts per power stage, which is a lot better. So this is the whole plan, and then we're going to see if we can lift up the power later to recoup some of that performance, because now we'd have 100 watts here, then again 75 plus 75, which is 150. It would be 250, but you still got to account for all the minor rails and stuff. So we're going to see how the card does, and if it needs further tweaking. But that's a pretty promising thing. And now the thing is, these two also tend to burn up on some cards, and I have a sneaking suspicion that, again, that's because we have 75 watts going through these two power stages. So the partitioning here is much smarter than it is up here. Okay, so here's the finished product. We have the 3 shunt resistors here. You can see that on the left, it looks a little bit thicker because those are technically 2 shunt resistors put in parallel. So that's the couple that does 2.5 milliohms, and on the right it's the original one. I had to put a little bit of Kapton tape on the back here to prevent them from shorting anything. But yeah, conceptually is exactly this design over here. I'm sorry, I had a little bit of acetone drip on here. It ruined the drawing. But yeah, here's the thing. It should now only be able to draw 100 watts through these 3 power stages, and that should do it. So now to reassemble the card and test it out. And again, my personal complaint with how NVIDIA manages things is that they are obsessed with monitoring how much current goes through each connector and the PCIe slot, but they apparently are not monitoring how much current is going through each power stage, which to me doesn't make any sense. I mean, you could group the connectors together and maybe have the PCIe slot separate, but the thing is, you should never overload any individual phase, or this is going to happen. Like, the card is going to blow up, right? So yeah, here's something for you, NVIDIA, if anyone is watching this video, if I'm that lucky. Try to monitor how much current is going through each DRMOS power stage and monitor their temperature. Okay, don't worry too much with the shunt situation, because all you need to do is not burn out the slot or the connector, which I see they've already failed at with the 4090, but that was mainly a connector design issue, not the card itself. But please be careful with the actual VRM, because the connector is much more stout and everything around it, it's much more stout than these tiny DRMOS power stages. And yes, these things are great, but they have a lot of power density, right? So thermally speaking, when you have individual high side and low side MOSFETs, far less problematic, because these things now push out a lot of heat on a small, tiny package, and you need a lot of phases to spread it out. But then if you don't load balance the phases correctly, this happens. So yeah, that's about it. Now I'm going to reassemble the card, test it out, and I think here goes nothing, because the card worked before, it's going to work now. It's just going to have a little bit less power on hand, and I'm going to try to tinker with it in Afterburner to get back that performance, and if it works and the card feels cool enough, then I'm going to flash it in BIOS and leave it at that. And I think the card is repaired, working, and should have its workaround. Keep it alive for hopefully the next few years. Okay, so right now the card is running, everything's stock except for our shunt mod. And the thing is, I can touch the VRM, which I really couldn't before. I can touch it from the back. And yes, it's really hot, but I don't instantly get burnt, because before I really couldn't touch it. So that's an improvement in and itself. And right now I'm running Unigine in the background because superposition is being stupid and doesn't want to make me run it in windowed mode, but I've run it in full screen mode, and this is a result from today with the power reduction, which is 3261 on 1080p extreme, and I've had a before test, which is 3441. So we did lose a little bit of performance, but it's not even 10%. So that's actually pretty good. And of course, you can see now perf cap reason is power, because the card thinks it's drawing 250 watts, but that's not real, and it's only going to 1140 megahertz, which before it could do like 12,000 and above. So we can try now maxing out the slider in MSI Afterburner. So let's try that. And we can go all the way to 1164. So yeah, still not great, and we aren't actually hitting a higher power limit, which I don't know why it's happening, but that's the thing. Anyway, even if it doesn't hit a higher power limit and we can't recoup that performance, I think it's still pretty fine. Especially the card is pretty silent and it runs well. So yeah, I think that's quite a success. It is warm to the touch. That's because the core is running. You can feel the memory. The memory is being pretty hot, but not terrible. And certainly it gets a lot more airflow like this than it did before. And mind you, that's at full load, full bore, no limits. So I'm quite pleased with the result, and hope this card will continue to work for quite a long time. But yeah, that's what a suboptimal design does to your components. And yep, that's pretty much it. Bye.